The goal of this lecture is to determine how to read the periodic table very quickly and to grasp as much information as you can in the most efficient and concise way possible. So this is a periodic table that I got from the internet. You can use your own favorite version. One thing I would recommend for the exam is to get a periodic table that actually gives the name of the elements. So this just gives the abbreviation. As an example, iron is Fe. It just gives the symbol, but it doesn't tell you that it means iron. So you may want to get a periodic table that actually gives you the full name of the chemical symbol. And the back, the inside front cover of your textbook also has a very nice methodical periodic table. First thing I want to tell you is going up and down in the periodic table. Okay, we're going to call those groups. Okay, so this can be called group 1 or group 1A, group 2, group 2A. Skipping over here, using the AB designation, again, it's specific to whatever periodic table is your preference. We can call this group 3A or 13, group 4A or group 14, all the way to group 8A, the noble gases, also known as group 18. So using the AB designation, the A's will be from 1 and 2, 13 through 18, and then when we go to the transition metal, these little big rectangular block in the periodic table, that gets the B designation, so 3B, group 4B, group 5B. So going up and down to the periodic table, it's called a group, and the name of the group, whether they use straight numbers, which you see here, or whether they use the AB designation, it just depends on what periodic table you will use. So going up and down is a group. Going left to right, a row in the periodic table, that's called a period, and it's designated by N. So this would be N equals 1, row 1, or period 1 actually, accurately. N equals 2 is period 2, N equals 3 is period 3, N equals 4 is period 4, so on and so forth. Some particular groups have special designated names, so I'm going to go over that with you. So we have a group 1 or group 1A, not hydrogen. Hydrogen is an outlier here. Group 1 or 1A are called the alkaline metals. Okay, so lithium, sodium, potassium, rubidium, cesium, and francium are the alkaline metals. That's another name for group 1 or group 1A. And if they're going to form a charged particle, they will be a +1 charge or a cation, a positively charged. So these elements, so what you see in the periodic table, very important, is not an ion. You're just seeing neutral Li, lithium, neutral Na for sodium. But if it were to become an ion, it would like to be +1. It would like to lose an electron to become +1. So group 1 or 1A are the alkaline metals. Group 2 or 2A are +2 ions. If they are to form an ion, they like to be +2. That is, they like to lose 2 electrons. The name for this is the alkaline earth metals. The alkaline earth metals. All right, let's move over here to group 16. No real name for group 16, does not have a special name, but I want to tell you that particularly with oxygen and sulfur in this class, they like to form -2 ions. So oxygen, if it were to form an ion, it would be the -2 ion, O-2, also known as the oxide ion, oxide anion to be specific. So O would like to gain 2 electrons, and if it does so, it will have 10 electrons. Group 17 or group 7A have a specific name, and they are called the halogens. Halogens unequivocally like to be -1. So F as an ion would be F-, Cl as an ion would be Cl-, Br as an ion would be Br-, I as an ion would be I-. These are called the halogens, and they're almost definitely going to have, as an ion, -1 in charge. Also important are the noble gases: helium, neon, argon, krypton, xenon, and radon. The noble gases are designated as noble. They are inert gases. They are royal in the sense that they're not very reactive. They will not form ions. Okay, so royalty in the sense that extraordinarily stable. So you may wonder, why does iron why does fluorine F like to be -1? Well, if fluorine F as an ion becomes -1, it will have 10 electrons. So F minus has 10 electrons. It has become noble in the sense that it has the same electron configuration as its nearest noble gas, neon. Right? Coming back to the metals here, why would potassium like to be a +1 ion? Well, potassium as a +1 ion, K+, would actually lose an electron. When it loses an electron, it becomes noble because it has the same number of electrons as argon, which is 18. That is its nearest noble gas. When it becomes the noble gas electron configuration, it becomes stable. So to ascertain that stability, the group 1 become +1 and the group 2 like to be +2. Along the same coin, the halogens, for them to be stable, because everything tends to drive towards stability, they like to be -1 because gaining that 1 electron, acquiring that -1 charge, makes them a noble gas electron configuration. All right, moving on here, this little rectangular block are called the transition metals. Some textbooks actually exclude zinc, cadmium, and mercury. Some textbooks actually include it, so I do not know whether to include it or not include it, but these are the transition metals. So transition metals are two important things about the transition metals that is definitely very important for this class. They're going to be plus ions, but they can be +1, they can be +2, they can be +3. We really don't know what charge a transition metal can take. As an example, iron +2 is the iron that's found in hemoglobin, makes our blood red. Iron +3 is the opposite. It's a different color. It's bluish or purplish in color. So iron +2 is important. That oxidation state is important to give a particular crimson color. Iron +3 will have a different color. That will bear importance for blood physiology. So iron can be +2, iron can be +3, chromium can be all the way to +3, +2, vanadium V, I've read, can go all the way to +5. So we do not know the exact oxidation state. It varies, it depends. Another thing about the transition metals is nomenclature. So nomenclature, we designate them by a Roman numeral. Many students miss this a lot in the nomenclature part of this course in Gen Chem 1. So when you're going to name these ionic compounds, iron 2 chloride, actually this is iron 3 chloride, so iron 3 chloride, you would designate it the Roman numeral 3 you would designate 3 via Roman numerals. Chromium 3 hydroxide, you notice the 3 is designated by Roman numerals. So anytime you name a compound, it's going to be with Roman numeral. The oxidation number or the charge is going to be designated by Roman numerals. This is not the case with anything else, any other area of the periodic table. Only with the transition metals are you going to use Roman numerals. Also want to bring your attention here, this row here and that row, the bottom row, have special names. I'm not going to mention them or lecture about them in the class, but these elements from atomic number 57 to 70, those are called the lanthanides, and from atomic number 89 to 102, those are the actinides. So the lanthanides and actinides are also in this sort of lower quadrant of the periodic table. It's something I'm not going to be lecturing you on. Speaking of atomic numbers, let's take a look at iron here, or just as well cobalt. That number here, 27 for cobalt, 26 for iron, 28 for nickel, 7 for nitrogen. That is the atomic number. Okay, the atomic number. The number of protons, and it is invariant. So as an example, cobalt will have 27 protons and 27 protons alone. It will never have 28 protons, because if it has 28 protons, we're no longer talking about the element cobalt, we're talking about the element nickel. Totally different element, totally different atomic arrangement. So this top number here in this version of the periodic table is the atomic number of protons. This number here with the crazy decimal, that is 3 definitions. One, and all three are equally important. The one definition is the mass number. So mass number is the number of protons plus neutrons. So the mass number for cobalt is 58.933. Usually we like to round it up to 59. So the mass number of protons and neutrons for cobalt is 59. The reasoning behind the decimal has to do with isotopes. Isotopes are the same element, different number of neutrons, but the neutrons and the different isotopic forms of the element add to the mass number. Okay? The best example of this is carbon-12 and carbon-13. So the reasoning behind all of these crazy and wacky decimals is isotopes, because there's going to be 1% or 2% of the cobalt that's found on this planet that has a different number of neutrons, and henceforth that 1 to 2% gets added onto your mass number. So that's why we don't have perfect round numbers here for the mass number. So mass number is definition 1. Definition 2 is weight in units AMUs. The AMU stands for atomic mass units. Finally, the most important relationship here for this bottom number is grams per mole. So it's the amount of grams in 1 mole of that element. So 1 mole of cobalt has 58.933 grams. So 1 mole of cobalt has that many grams. Okay? On the flip side, 1 mole of zinc has 65.39 grams of zinc. So if I were to go and get the purest zinc possible, elemental zinc, and weigh out 65.39 grams of that zinc, it's the same thing as 1 mole of that zinc. So this is something that's very important that students, based on my experience, generally have a little bit of a difficult time grasping. So it's going to definitely take a little bit of time to understand that grams per mole concept, which is symbolized by this bottom number, one of the 3 definitions. Let me give you another example for copper. Okay, Cu. So imagine I go out and give you as a gift 63.545 grams of copper. It's the same thing as me gifting you 1 mole of copper. So 1 mole of copper is equal to 63.545 grams of copper. 63.545 grams of copper is the same as 1 mole. That's a conversion factor. That's used a lot in dimensional analysis or conversions. A couple of other organizations are sort of dissecting the anatomy of the periodic table. This little staircase here, all right, it separates the metals, which are to the left-hand side, shown in blue here, with the non-metals, shown here in sort of this reddish-pink color. Those elements in these boxes that are touching this staircase are known as the metalloids, which I'm not going to talk in great depth about, but the metalloids, boron, silicon, germanium, all these guys here that sort of straddle the staircase, they have properties that are reminiscent of metals, and they have properties that are reminiscent of non-metals. So they are both a mishmash in terms of properties, chemical and physical properties. They are a mishmash of metallic character as well as non-metallic character. Some characteristics of metals, properties, there's a big theme here in general chemistry. Very quickly, metals are hard. Okay, metals have a very hard, rigid atomic structure, almost lattice-like. Metals are not so much malleable as the non-metals, but metals are very rigid and have a very rich atomic framework. Another thing about metals is that they conduct electricity. So you can make a wire, such as copper, and have electrons flow through it, sort of a conduit of electrons. So in that perspective, metals are conductors. All of these properties are exactly the flip or the converse for nonmetals. Nonmetals are not hard, they are soft, they are malleable. Nonmetals are not rigid. Nonmetals are non-conductors. Nonmetals are usually gases. As an example, oxygen is in O2, that is we breathe, which is a gas, O2 gas. So the natural abundance form of oxygen is the O2 form. It's not a metal. So then it's not hard and it's not a conductor of electricity. So those are the general characteristics of metals and nonmetals. The periodic table is divided and splits between those that are metallic and those that are non-metallic, with a couple of elements that cannot decide. Metals give up electrons. Remember the alkaline metals group 1, the alkaline earth metals group 2A, they are +1 ions and +2 ions respectively. So they like to give electrons. Okay, this first group likes to give 1 electron to be noble. The second group likes to give away 2 electrons to be noble. So in that regard, metals are electron givers. And who are the takers? Non-metals. Halogens love to be -1 and gain an electron. That's how they acquire nobility. The same electron configuration of its nearest noble gas. Oxygen and sulfur love to be -2. They love to gain 2 electrons to become quote-unquote noble. So while the metals are the givers of electrons, non-metals are the takers of those electrons. So in that regard, metals will react with non-metals. We call that an ionic compound. Non-metals can react with other non-metals. Classic example, carbon dioxide, CO2. That's a non-metal carbon reacting with 2 atoms of oxygen, CO2. So that's a covalent compound. Electrons are shared. Okay, so double bonds, single bonds, triple bonds. Those happen within nonmetals. That's a covalent compound, sharing of electrons. Metals with a nonmetal, those are ionic compounds. Those result in a transfer of electrons. Literally, the metal is giving an electron. The nonmetal is usurping or acquiring that electron. You get an ionic compound. Nonmetals with nonmetals, sharing. Sharing is caring. They share electrons. Like I said before, that's how you get your double, single, and triple bonds. Finally, the last bit of information that you can get from the periodic table is the blocks of electrons. This will become important when we talk about electron configuration in the course, but just for now, just want to tell you that group 1A, alkaline metals, group 2A, alkaline earth metals, are the S block of the periodic table. That is to say they have S electrons, and those S electrons are going to occupy the S orbital. The transition metals have D electrons, and then this is the P block. So these are the P electrons, and these have 3 orbitals. Each orbital holds 2 electrons. They pair, and so the P block can actually hold the P block can actually hold 6 electrons. The D block can actually hold 10 electrons, 5 orbitals, each holding 2 electrons. The S block is 1 orbital, each holding 2 electrons, so the S block holds 2 electrons. This will become important when we talk about electron configuration